Hi, I'm Anton from Anton's Mindstorms Hacks. Today I will be discussing power and speed with you. By the end of this movie we will be able to calculate the speed of this robot in kilometers per hour. For this we need to understand the concept of power, the concept of speed, which is both linear speed and rotational or angular speed. Power can be a little confusing in the LEGO Mindstorms interface, so there is some explaining to do there. Let's get to it. For this video I will be using the education version of the LEGO Mindstorms software. Even if you have a retail set, you can still download and use this software. I'm using this version of the software because it's got not only programs, but it's got an experiment module which we can use to log and plot data, and we will be using the data log to show the difference between power and speed in a LEGO Mindstorms program. So let's start here with a little loop, and in this loop we are going to make a 100-second loop. So if we wait 100 times, so we will loop 100 times over the wait block, so this will take 100 seconds, and during the length of this loop we will use a regular motor block, let's say port B, and we will turn on that motor and use the loop counter as an input for the speed. So the first time, in the first second, this will give a power of 0. The second time around it will give a power of 1. So we will have a gradual power increase here on the motor B. And during that time we will be data logging, and we will be logging the motor rotation in degrees of port B. Of course, we will also be logging the motor power at port B. So we will be logging power, actual power, and degrees over a 100-second loop where we increase the power every time, and then from there we can derive what power and speed really means within LEGO Mindstorms. Okay, the robot is connected. Let's run the program. What you can see is that this motor here slowly starts spinning, and it will take 100 seconds to finish the program, but you'll also see that it will take much sooner to reach top speed. It slowly spins faster and faster. You can hold your mouse button or your mouse pointer actually over the wire, and you will see the data in the wire, and right now we're at 60 power. Let's see, this is power for the motor, 75 power, and my experience is that at about 75, 80 something, the speed doesn't go up very much. Yeah, I think we reached top speed now, because you can hear the motor running, and the pitch of the whine of the motor, the pitch doesn't increase very much anymore, about 80-85. Okay, and 97, we reach 100. The program is done. Let's go to the experiment and see what data we got from motor B. In the experiment here we chose the upload button, and there's my power speed program, and here is my data which I'm going to import. Okay, Here we have a 100-second time frame, where you can see that, yeah, like much as I heard a bit above 80. The speed power doesn't really increase anymore, which is strange because we measured power, but then the data log power, even though we input more than 80 into the speed block, we don't get any more power back. The other graph really is the degree in rotation, which is a hyperbolic curve. Let's see if I can show you the maximum. 50,000, yeah, that's about 50,000 degrees that we run by the end of the 100 second. So you can change the scale here, but we are not actually interested in the total amount of degrees that we run by the end of the program. We are more interested in the in the derivative of this curve, because if, at any time we see in any little time gap, we see what the change was in degrees. That means that we get the speed, and there is a really nice formula for that. So we can take our degrees here, and we can there is a formula here called derivative, which is funny again in the user interface because I click derivative but I get the slope function. Anyway, they are synonyms, and we can calculate the slope here, and the slope of our degrees is plotted in black. Let's change the colors a little bit here because it's confusing. So let's make the degrees red, the power, the measured power, let's keep it purple, and let's make the slope of the degrees curve, so that's the slope of this red curve, let's make it green, and we want to have it to run from 0 because it actually starts at 0. I think it goes up to about 800. Oh, even higher, 1000. Yes, 1000. 1000 is the maximum number here, and you can see that the curves more or less overlap, which is interesting, and which also leads to the conclusion that LEGO here made the interface, the user interface, a little confusing, because what we are seeing here in green is the derivative of the red curve, and the red curve is position. The derivative of position is speed. Okay, so the green curve is speed, but in the data log we also measured power, and the power is a curve that goes very much overlaps the speed. So the conclusion here is that LEGO actually called speed power, which is very strange because in physics power is a very, very different thing from speed. Power is really the amount of energy you can convert per unit of time. So if you say you climb a ladder of 5 meters in 3 seconds and you weigh about 100 kilograms, that would mean that you are able to convert the energy from the breakfast that you ate into climbing energy with a rate of 600 watts. So watt is really the unit of power. Okay, what we are seeing here, the green curve, is that the speed of the large EV3 motor tops off at about 840 Can you read the data? I think I can see it here on the left side of my screen. It tops off at about 840 degrees per second. It also leads to a conversion rate. When LEGO says a motor is running at say 84, 85 power, it means you're running 10 times that amount in degrees per second. Now that we know what the conversion rate is, we can easily make a speed measure for our robot. We will start with a loop, and within that loop we will constantly measure the motor power. Since the motor power here is in LEGO style power, but it's actually speed divided by 10, we will do some calculations. So from this wire on, okay, if we multiply it by 10 we will have degrees per second, and degrees per second is not so interesting because we want to drive the robot on the floor or over the table and want to know what its speed is in kilometer per hour. So we will have to multiply the degrees per second by a certain factor to get millimeters per second. And I will be using advanced math to do that. So the number A here is the degrees per second, and I'm going to multiply this by the first is degrees per second, so I'm first going to divide it by 360 to get rotations per second. Every rotation moves the motor by the circumference of the wheel. So if we multiply rotations by the circumference, we get the speed, and the circumference is pi 3.1415 times the diameter of the wheel, and my wheels are, let's see, 62.4 millimeters. So right now this equation gives me the speed of my robot in millimeters per second, which is nice, but maybe not so interesting as kilometers per hour. So to get from millimeters per second to kilometers per hour, we have to divide it by 1 million. So if we because there are 1 million millimeters in 1 kilometer, and now we have kilometers per second, but nobody drives cars at kilometers per second. We want to drive cars at kilometers per hour, so we will multiply this by 3600 because there are 3600 seconds in an hour, and then we get our speed in kilometers per hour. Now this calculation we will plot to the screen. Put it in text mode, set it to wired, and show my result on screen. And now I I run my program, and on screen I push around my robot. I get around 1 kilometer per hour, 1.5 kilometer per hour, and maybe 1.9 kilometer per hour if I push it really fast. So here you have it. This program converts the LEGO power, which is actually speed, to an interesting unit, kilometers per hour. Now we can also power the motor that we are using. So let's use a regulated block here, and let's run the motor at 75 power, and let's see what this gives us. Okay, This means we are running 1.4 kilometers per hour here on the robot at 75 power. We can run it even faster at 85 power. .6 kilometers per hour. Awesome. Now let's go all the way up to 100 power here. Still 1.6 kilometers per hour. So the last 15 power on a large motor block, they don't really matter. They don't increase the speed of your motor anymore. This concludes my video for power and speed. As you can see, it's if you know how, it's not that difficult to calculate the speed of your robot in kilometers per hour. The blocks in the LEGO Mindstorms interface are just a little confusing because they have been calling power, they have been calling speed power. So while in normal physics and engineering, power is the rate at which your machine can convert energy from one kind into another, say electrical energy into mechanical moving energy. In the LEGO interface, they just meant speed. Because speed is a number from 1 to 100, in the LEGO interface there is a conversion factor. For the large motor, it's really easy. It's just times 10 to have degrees per second. If you, I haven't actually measured the medium motor, and if the medium motor also has a times 10 rate of conversion, I think it will be different, because in the medium motor I suspect there is a different motor and gearbox. So it's up to you to measure the LEGO power to speed constant for the medium motor. Good luck and enjoy building robots. Bye bye.